Welcome back to the deep dive. Today we are strapping in for a high voltage ride into the world of industrial design documentation.
That's right.
We're pulling apart a set of instructional materials that are specifically made to train electrical engineers on AutoCAD Electrical.
If you think about a modern factory or a skyscraper, you're dealing with literally thousands of components.
Okay.
Motors, sensors, relays, all of it.
All working together.
Exactly, in perfect harmony. And our mission today is to analyze the blueprints for that harmony. We want to extract the fastest path to understanding how you read and design these things.
Okay, and the first thing the source material points out is it's actually less about the software and more about the person using it. Let's talk about the prerequisite. What's the non-negotiable cost of entry here?
It's the language itself. I mean, the course just assumes, and it's a correct assumption, that you already have a strong background in electrical components.
You have to know what you're looking at.
You have to know the symbols, the terminology. If you can't instantly identify a normally closed contact or a fuse symbol just by its shape, then the software is.
Yeah.
It's basically useless to you.
So the software helps you draw, but it absolutely does not teach you electricity.
Not at all.
That's a huge distinction. So the biggest hurdle isn't learning a new program, it's that you have to master this whole other alphabet before you even launch the application.
Right.
Okay, so let's unpack this. If you already have that foundational language, why are these drawings even necessary? Why can't an expert just, memorize the whole system?
Oh, because of the sheer scale.
So.
It's not possible. Imagine an automated packaging line. You might have 20 motors, hundreds of relays, sensors everywhere.
Yeah.
You just can't remember all the attributes, the wire gauge, the voltage rating, the specific catalog number for every single one. It is completely impossible.
So the drawing is less about a picture and more about data management.
That's the perfect way to put it. Its primary function is data management. It lets an engineer find, track, and manipulate all those incredibly complex relationships.
Okay, so that makes the drawing more of a navigable database than a static image. Which brings us to the first essential skill, reading the language.
Absolutely. Reading the drawing is step one. It's the foundation. If you can't identify a component and its symbol, you have no chance of creating one.
And we're talking about everything from a simple push button to
really complex devices, things like VFDs, variable frequency drives, which, manage a motor speed and torque.
So for a VFD, what kind of data does the drawing need to capture? It's got to be more than just a symbol.
Oh, yeah. For a VFD, you need to know its control voltage, what motor it's tied to, its capacity, and critically, how it fits into the whole system's logic.
Okay.
And that leads right into a core structural idea that the material really emphasizes, the concept of parent and child components.
Parent and child. Okay, tell me more about that. How does that relationship help manage all these references?
So think of a relay. The relay coil itself, that's the parent. It's the physical thing you buy and install.
Right.
Now, that one single relay might have 4, 6, maybe 8 different contacts. Those are the child components. And they could be spread out all over the drawing.
On different pages.
On completely different pages. One contact might control a motor. Another one turns on an indicator light. A third could be part of a safety circuit.
Oh, okay.
The parent component holds all the catalog info, the physical data. And every single child contact, no matter where it is in the 50-page drawing, it automatically cross-references back to that parent.
So if I'm on, say, page 10 of a schematic and I see a contact labeled CR104.
The drawing will tell you right there that the main coil, CR10, is on page 4.
And the software just handles that automatically.
Seamlessly.
Yeah.
It ties the physical part to its logical function across the entire project.
Yeah.
Without that parent-child relationship, you'd be manually flipping through hundreds of pages just to figure out what's controlling what. It's the structural heart of the whole thing.
That kind of contextual awareness that's what really separates this from just a standard drafting program.
Okay, so moving into the actual architecture, what are the two most fundamental building blocks of these drawings?
It's simple, really. Wires and components.
That's it.
That's it. Every single action, every command, it all boils down to creating, connecting, and manipulating those two core elements.
So for someone learning this, the source materials lay out a kind of roadmap of skills. What are the really critical functions you have to master?
Well, beyond just placing components, it's about managing big chunks of standardized logic. So first, you learn the fastest ways to wire things up, often using these intelligent multi-wire buses.
Okay.
Second, you have to master working with ladders and circuits. The ladder diagram is just standard industry practice for controls. It makes things easy to read.
They're like the scaffolding for the control logic.
Perfect analogy. And then what about the brains of the operation, the automation?
That would be the PLC. Exactly. The third skill is using PLC symbols, programmable logic controllers. In any industrial setting, they're the brain. They can have hundreds of input and output points.
I can't imagine drawing all of those manually.
You don't. The software lets you generate huge blocks of PLC I/O symbols almost instantly. It saves weeks of manual work and manages all the connection points and addresses automatically. And finally, you learn to create panel drawings, which show the physical layout inside a cabinet.
It really sounds like the whole point is to automate the most repetitive parts of the job and, I guess, ensure data integrity.
That's it.
So that raises an interesting question for me. If all this complexity is being managed, the parent-child data, the wire numbers, all of it, is the visual schematic just a means to an end? Is the engineer more of a data manager than an artist?
That's a fascinating way to put it. And yeah, increasingly that's true. The most important end product isn't always the beautiful drawing itself.
So what is it?
It's the data that's locked inside it. Which brings us to the most critical output that the sources emphasize: reports.
So what's factor? I'm guessing the bill of materials is king here.
The bill of materials, or BM report, is the final authority. It is everything. It's what the purchasing department uses to order parts. It's what the assembly team uses to build a machine.
Because every symbol is intelligent.
Right. Every component you place carries its catalog number, its manufacturer.
Right.
All that data. So the software can, in an instant, generate a perfectly audited list of every single screw, wire, coil, and motor in the entire project.
So if a designer messes up the BAM,
the build stops. Or you order a 24-volt component when you needed a 120-volt one. The BM validates everything. It ensures the count is exact across every page. That's why companies pay for this kind of specialized software.
It's the linchpin of the whole project lifecycle.
Sure.
Okay, let's switch gears. Section 3. Navigating the software itself. I open AutoCAD Electrical for the first time. What am I looking at?
So typically the default view will pop up a demo drawing. And that's actually really important.
What is it?
Because it immediately shows you what a professional drawing is supposed to look like. It's got the title blocks, the formats, and examples of those reports we just talked about. It gives you the target right away.
Okay, so we're oriented. Now here's where it gets, I think, really useful for our listener. How does AutoCAD Electrical separate its own special commands from the hundreds of regular AutoCAD commands?
This is a brilliant design feature. It speeds up your workflow so much. All the standard AutoCAD commands, line, copy, limits, they're all still there.
The ones people already know.
Exactly. But, and this is the key insight, any command that is specific to schematic design, to wiring, to components, it's prefixed with AE.
AE for AutoCAD Electrical. That's the designer's secret code.
That's the code.
Okay, so give me an example. What's the difference if I use the regular trim command on a wire versus the AE trim command?
Perfect example. If you use the standard AutoCAD trim, you just cut a line. Poof, its intelligence is gone.
So it's just a dumb line now.
It's a dumb line. The program no longer sees it as a continuous wire. You lose the tag, the connection data, the numbering sequence gets all messed up.
Which means your Bezier is now wrong.
Correct.
Yeah.
But if you use AE trim, the software knows you're cutting an intelligent object. It cleans up the wire, it makes sure the remaining segments are still tagged correctly, and it updates the wire numbering instantly.
Wow.
The AE commands preserve the underlying data structure. That's the whole point.
So general commands move geometry, but AE commands move and edit data.
That's it exactly. It completely changes how you interact with the drawing. You're manipulating a database, not just a picture.
The sources also mention workspace management, like customizing your tabs and things. Is that important for a beginner?
No, not at all. That's expert level stuff. For a beginner, the default is fine. Optimizing your screen real estate is something you do way down the line once you're proficient and you're juggling different clients and projects.
Right. Competence first, then efficiency. Okay, let's look at the content of the drawings. The design seems to be structured around two different kinds of circuits. How do you tell a power circuit from a control circuit?
They do two completely different jobs. Power circuits are the heavy lifters. They handle the high voltage lines, the energy that actually runs the motors.
So big components, breakers, motor starters.
Exactly. They're all about current and voltage capacity.
Yeah.
The muscle.
And the logic side.
That's the control circuit. These circuits use really low current to tell the high voltage circuits what to do. They're the brain. The nerves. They deal with things like contacts, relay coils, push buttons.
So understanding the difference between the muscle and the nerve is fundamental to reading the whole system.
You can't understand the drawing without it.
Now, with modern systems, you're always going to need components that aren't in the standard library.
Yeah.
The sources mention creating custom blocks.
Yeah, that's a constant reality. You have this huge library, but industry innovates so fast that designers will always need to create their own symbols.
So how do they do that?
There's a tool called the Symbol Builder. It lets you take a simple AutoCAD block, just a basic shape, and turn it into an intelligent component. You add placeholders for all the catalog data, wire connections, and the cross-referencing capabilities.
So the designer is constantly adding new words to the software's dictionary.
They have to. It's an unavoidable part of the job if you want those B-Ball reports to be accurate.
Finally, let's talk standardization. This seems to underpin the integrity of the whole system.
It's completely non-negotiable. Your drawings have to follow established industry standards. So in North America, that's usually ANSI. Internationally, it's often IEC.
And those standards dictate everything.
Everything. The look of the symbols, the way cross-referencing works, and crucially, the measurement system metric or imperial.
And you set this at the very beginning of a project.
Right at the start, in the project settings menu. The sources say this is absolutely critical. If you drop an IEC symbol into an ANSI project, the dimensions will be wrong, the references might fail, the whole thing just breaks.
A mistake there could just cascade through the whole procurement and building process.
You could halt it completely. You're setting the rules for the entire data set from the very beginning.
So what does this all mean? Our deep dive really confirms that managing this industrial complexity is all about turning a blueprint into a powerful relationship-based database.
Exactly. And the entry ticket isn't knowing the software, it's knowing the language of electricity first. The basic building blocks, wires and components, are made intelligent by those specialized AE commands that protect the data.
And that protected data flows into the ultimate goal, the Critical Bill of Materials report, which links the design directly to the real world of purchasing and manufacturing.
And the whole structure is held up by that mandatory standardization.
Yeah.
Power circuits, control circuits. They all have to speak the exact same language, following the same rules.
It's a world where logic and data integrity are king. And that leaves me with a provocative thought for you to think about. If the integrity of a billion-dollar industrial facility hangs entirely on the accuracy of that Bill of Materials report, and that report is based on symbols that engineers frequently have to custom build, does that reliance on constant customization actually create a bigger point of failure than the standardized library itself? And what does that tell you about the speed at which industrial parts are evolving, maybe even faster than the software can keep up? Think about that. Until the next deep dive.